This lecture is going to cover two-dimensional and three-dimensional models used in remote sensing and rasters and terrain. These are the topics that we will cover: vector versus raster, surface consideration, topology, including drainage networks, watersheds, viewsheds, volume, which is a technique of extracting change difference between two rasters, digital elevation models, including slope, gradient, and aspect, triangulated irregular networks, two-dimension models of contours, shaded relief called hill shading, and three-dimensional models using helicopter and ground data or drone technology. And I will briefly cover model considerations for projects. So here is a comparison of the same spatial area shown with different data structures. So in the upper left-hand corner, we have elevation, which is based on meters above sea level. Slope is the change in that elevation. Hill shade has to do with the shading that makes your data look like real-world features, and aspect has to do with the direction of the facing slopes. The bottom ones include multi-directional hill shade, an aspect map that's been colored, a slope map that's been colored by an analyst, and an elevation tinted hill shade. So these are just some different types of data structures, and you can see that taking our gray pixels are bits of data, and by color coding them as a GIS analyst, you're able to display the information in a more vivid way. A surface is a geographic phenomenon represented as a set of continuous data. So some types of data that you would see displayed as a surface would be elevation, geological or rock type boundaries, or air pollution. Temperature could also be one, sound, and essentially it's a spatial distribution which associates a single value with each position in a plane. And this is usually associated with continuous attributes. So they're not discrete objects. They tend to be data that varies across a continuum. A surface model is a representation of a graphic feature or a phenomenon that can be measured continuously across some part of Earth's surface. Here we see an example of elevation, and you can see in the table of contents that we have low and high values, and the higher values are reds and oranges. The low values go down into the shades of blue, and surface models are stored and displayed as rasters, tins, or terrains. I encourage you to look up key terminology in the GIS dictionary, and in fact, this is a good source to bookmark and keep handy, as it is very useful in showing not only vocabulary and definitions, but there are often graphics and images that help with learning new vocabulary. Okay, so back to the lecture, sources of surface data. They can come from point surveys, photogrammetry, interferometry, which is collected from radar imagery, usually flown on small aircraft, altimetry. You can capture contours digitally from an analog map. You can use aerial imagery and topography, and you can also use survey points and perform interpolation on them, and that will give you a surface. Here's an example of a drainage network and watershed. So the topology is a set of topological relationships or rules between coincident parts of simple features on a map. This is used to share and edit shared parts of multiple features. So you can see here, this is Harris County's watershed, a map layout on the left, and then in the middle, we're looking at an analysis of flow, and flow would be a direction that water is going to move in a watershed. And so you can see that flow is calculated for every cell, which is based on the direction of the steepest slope. So on the left, in those squares, we have elevation values, and then on the right would be the flow direction that's been calculated based on the values that you see on the left. And then finally on the right is another model map, and it is showing development pressure coded as high and moderate within the Chesapeake Bay watershed boundary, and it's also showing some land cover. And watershed delineation is based on the contribution, direction, and sources of cells in a grid. And this makes sense intuitively because water is going to behave according to the areas around it. So we know water flows downhill, and we can use information in order to determine the behavior of a watershed and the drainage network contained within it. So here's some examples of topology viewsheds. So on the top we have the viewsheds of the digital elevation models. The first one on the left is collected with LiDAR, and then we have 10 meter, 30 meter, and then 30 meter shuttle range topography mission data. At the bottom we are looking at the difference between the DEM and the manual viewshed. So again, this is analysis of a viewshed, and it is performed using GIS tools. When we think about volume, we can estimate volume of a quantity related to an area. So this is very, very useful in looking at reservoirs, for example, or perhaps the amount of soil and rock that would be needed to excavate for a railway line. There's many other applications. Those are just a couple of common ones. And it's basically a cut and fill analysis. So in this illustration, we have a before raster and an after raster, and the difference of those two is our output raster in blues and purples. So here's an example of a project that was done in China, and it is the Wusong Riverfront, and it's a cut and fill study and soil conservation study. And so they're looking at analyzing geologically the removal or the cut and fill of the land in order to contribute to soil conservation. So there is a YouTube video on how to calculate volume in using ArcScene, and I encourage you to come back after you view this lecture and view this YouTube video on calculating volume. For time's sake, we're not going to do it right now in lecture, but it is here, and all you have to do is access that video, and it will take you step by step through how to calculate volume. With photogrammetry, you can use metric interpretation of image data. This is showing you some simple equations for flying height, and the flying height or the altitude of the aircraft affects the imagery that you'll have, and you will need to be able to interpret that data based on simple algebraic equations like the one that you see here, where the height equals F over S. So what is photogrammetry? Considering two different types, topographic and close range. Topographic is used for mapping Earth or planets based on an aircraft or spacecraft. The target is the ground surface or Earth's surface, and image data is processed to create new spatial information products. Whereas close range photogrammetry is used for industrial measurements. The systems are handheld, and the target is the object being measured, and image is more precise. Image data, that is more precise. So here's an example of metric interpretation of data, and certainly no need to memorize something like this. Again, we're talking about models, and so as you start putting the final hours into your project, I want you to think about data acquisition. And this is an example of photogrammetry, which we don't use in this class, but it is useful to look at the different types of equipment used and the workflow that is drawn out. And then there are photogrammetric products, which would be your outpoints or your outputs in a GIS. And think about your workflow. Some Excellent project examples have put their workflow in a flowchart or a format like you would see here with arrows. And that's something to consider when you're reporting in your project. So remember, for this class, it can be short, concise, and you aren't doing a written paper, you're doing slides, PowerPoint slides. And so this is a really great way to show workflow. Interferometry is a technique where waves are superimposed and then information is extracted from that. So radar sensors send out their own microwave signals, and this allows them to interpret or see, in quotation marks here, how they backscatter dependent on relative surface roughness. So one great advantage of radar instruments is that they are not light dependent, meaning they can collect information through clouds or darkness. And the schematic on the left here shows an example of how interferometry is collected with a detector and a series of mirrors, and then the light source on the left. Here's an example of a map made using differential interferometry. And so 2 radar images were taken at the same site, and the equipment operates at very high frequencies and a corresponding low wavelength. Only 5.6 centimeters in the case of ASAR, and that means a complete cycle through a signal wave occurs for every 5.6 centimeters of distance. And then the division of that total distance that the signal travels from space to Earth and back again by its wavelength determines at what fraction along a peak or trough of a wave the returning signal will be. And this value is known as the signal phase. So this is an example from Naples, Italy, and it is an interferogram. So more about interferometry. If the same target on Earth is reacquired from the same point in space using radar, then in theory, the total signal distance should remain unchanged and the signal phase should remain the same. And so this image of an interferogram was collected using synthetic aperture radar, or SAR, and the images were collected at 2 different times, and they have a surface deformation, and that means that changes may have occurred during the time between data acquisition. So interferometry is very popular in earthquake, geological, and landslide studies. Here's an example of the deflation of a volcanic summit, and this is Kilauea Summit. This is not the most recent deflation of Kilauea. It is aged, it's a few years ago. I do know that this slide was made before the 2018 eruptions in Kilauea. But this image was made with an interferogram from radar data. The colored fringes that you see in purples and blues and greens show deformation of the Earth's surface towards or away from the satellite. And so you can see in this image that there are more fringes clustered together in certain areas. That means more deformation has occurred. Each color cycle is equivalent to 1.5 centimeters towards or away from the satellite. And there is a scale bar there that shows what each of those colors mean. So this actually occurred between May 8th and May 11th, and it has a magnitude of about 25 centimeters over time period spans. And there's no obvious deformation of Kilauea's East Rift Zone, and the fringes in the vicinity of the area or the crater called Pu'u'o'o, it shows topographic errors caused by lava flows that were erupted over the past several years. And again, the fringes on the volcano's south flank between the summit and the ocean are probably caused by atmospheric conditions. So it's not necessarily a movement of the Earth, it can be atmosphere as well. But there is definitely a deflation of that summit, and it is shown very well with an interferogram. Moving on to altimetry, it is defined as the measurement of height or altitude. This is an example of the TOPEX Poseidon mission. It orbits Earth at about 830 miles above the surface. On board is a radar altimeter that measures the height of the sea surface to an accuracy of less than 2 inches, which is pretty phenomenal. If you're getting that much accuracy from 830 miles away, that's pretty phenomenal technology. And it would be like measuring the thickness of a dime from a jet that was 35,000 feet up. So the altimeter transmits radar pulses towards the sea surface and times how long it takes for each to get back. Every 10 days, Topex Poseidon makes a map of the height of the ocean. So oceans are not flat and they don't all have the same height. And this is one of the ways that we keep track of that. You can also digital capture from analog maps using heads-up digitizing, scanning, and user input. So here's an example of aerial imagery and topography put together. This is surveys from the Sandy River near the Marmot Dam and from 2008. So it is showing blue points are fixed cross-sectional surveys, and these are repeated every year, and orange points are based on topographic surveys that map out significant features, including the water's edge, slope breaks, etc. And then the dark orange lines are connecting points that are tracing common features like a river channel or sandbar. So interpolation by survey points is collecting values at known data locations, and then from those samples you can predict unknown values for your whole study area. And this is useful for data such as elevation, rainfall, chemical concentrations, and noise level. So you can see here in the squares, it's showing representative data that would be collected at each of those blue points. And then from that data, the values are interpolated by a GIS system, and you can see the resultant surface in shades of brown. And then on the right is an example from open source GIS, which is QGIS, and it's showing elevation. So when elevation maps are created, even if they are using handheld devices to look at data, they do not take an infinite number of data points throughout the study site. They only take samples. So here's an example of the interpolation of rainfall. And so you can see that there is input rainfall point data ranging from 14 to a high value of 30. So these are known rainfall level values. And then on the right, it would be an interpolation of what the predicted rainfall would be for each of those pixel areas. And it's predicted with a mathematical formula that takes into account the data that you see on the left. So here's an example of an elevation surface that's been interpolated, and again those blue dots on the left represent known areas of elevation, and the point interpolation is used to create the elevation surface from those sample measurements. And in the following graphic, each symbol represents a location where the elevation has actually been measured. This is done with GPS units. And then you interpolate and you create the surface on the right, which would predict values for elevation throughout the entire spatial extent shown here. Here's an example of ozone monitoring in the state of California. So each of those blue dots represents an area where the ozone concentration was measured in a study on lung disease in California. The image on the left shows the interpolated surface, and you can easily see the areas of high risk, and this is a technique that is known as kriging. A digital elevation model is a representation of continuously sampled surface of ground height above a datum, and it is a way to depict the variations of physical land features on the Earth. So how is it generated? With radar interferometry, there are two receivers, and you can see that there is a transmitted wave shown in green and a received wave shown in red. It can also be collected from airborne or satellite remote sensing, as we discussed above. And then the stereo images are combined with radar and LiDAR data used to process and create a digital elevation model. So DEM, DTM, and DSM are related terms, and we're just going to talk about the subtle differences. They represent the uppermost level of a feature, including buildings and canopies. So um, the digital terrain model, or the DSM model, will remove buildings and vegetation and actually represent bare earth. So here we see a digital surface model on the left in red and the digital terrain model in green. And the green line does not take into account the tops of the trees or the building surfaces. So from a DEM, which we see in the center here, you can run tools in ArcGIS and get aspect, slope, hillshade, and then the one on the bottom is the same one on the top on the right side. It has just been tinted, or a color ramp has been applied in order to show that hillshade. And so aspect has to do with this direction that the slopes face, and then slope is how steep an area is, and then again that hillshade is showing variations in land features like we would expect to see with our naked eye. TINs are triangulated irregular networks. They're used for surface modeling. You can see here there's a series of triangles, and it is a connection of XYZ points. The edges are actually forming those networks of triangles, and they're used to represent the surface of a geological unit or the surface defined by a mathematical function. So here is a 2.5 dimension and 3-dimensional image constructed from selected minimal data point collection sites. So on the left, you can see the point data is where values were actually collected. And then on the right is the 3-dimensional TIN, or triangulated irregular network. So TIN versus raster. Well, a TIN actually produces a more realistic visual representation, and the multi-quadratic radial basis function generates more accurate representation and measurement of slope than a raster. So just looking at these two comparisons here side by side, you can see that the TIN is more complex and shows more subtle variations in the elevations than your raster would on the right. Here's an example of a TIN created for southern Okanagan, and the elevation ranges are shown in the legend on the left. Here are some geographic features in spatial data. We have a digital terrain model, an ortho image, a digital surface model, and then we have a topo map on the bottom left, and this was manual contour extraction, and topographic maps typically have that kind of color combination with brown topo lines, and blue represents water bodies, and then in the middle bottom we have digital elevation model, and then on the right is a digital surface model with vegetation. So geospatial models are a way for us to represent our interpretation of geospatial reality. And so we can have a raster model with the pixels shown in this top layer. We can have a vector model shown in the middle. It's the same geographic area, and then at the bottom is an artist's rendition of what the real world would look like. And you can see the faint lines on there representing the combination of raster and vector models put together. So when we compare points and pixels and lines and areas, a point and a pixel represents discrete geographic features. They're countable and they're of a limited area, such as buildings or data collection sites. Lines are linear features of many points that are connected together, and this would be things such as roads or rivers. And then areas are closed lines, and these features represent shape, area, and location of homogeneous features such as land use, buildings, or rock types. And so in these images here, you can see the difference between points, roads, and areas or polygons, and we're representing buildings, roads, and land use areas. And then on the right would be the raster model equivalent of that vector model point, line, and area feature. Here's an example of reality on the left, and then a vector model of reality on the right. So you can see that there are different land covers represented here: forest, corn, soybeans, and hayfields, and then they are given names on the vector model on the right. So again, here's an example of coding raster GIS data, and you can see that forest has been coded with the number 1, corn is 2, soybeans are 4, and the house is number 6, and then the hayfield is 5. So this is a way of taking and putting metadata or putting codes to what each of those pixels represents. So a surface model phenomenon that varies continuously across an area, such as elevation, precipitation, temperature, or magnetic susceptibility. So that's, again, another definition of a surface model. It looks very similar to the definition of a surface because it is just a model in a GIS built on surfaces. And a surface will describe statistical representation of the magnitude of the variable, and this takes into account the range, and it is often and accurately termed statistical surface. So here are 2-dimensional and 2.5-dimensional and 3-dimensional ideas. So if we look at the map image on the left, if you can see the title, it says geometric data with bridges, and it is pretty flat, and there isn't a good sense for the actual landscape features, and so surface data is sometimes referred to 2.5-dimensional data because it really only supports a single z value for each x location. But if we look at our LiDAR data on the right, you can see that that bridge actually has several z values. It looks like there are 2 separate areas where cars can drive on that bridge, and then there are structural beams overhanging the entire bridge. So again, and lots of crossbars and beams and cables and things like that. So there's several z values for each x and y location, and that's truly 3-dimensional. So 2-dimensional would be contours and hill shading. We've seen examples of those before, and here is an example of shaded relief at a 1 to 1 million scale from the Federal Office of Topography. And then we have raw shuttle range topography mission data in the middle. And then on the right, we have the data that was generalized with Terrain Sculptor. So a Terrain Sculptor is a tool that helps smooth out the data, and it's for appearances, for mapping. Here is an example of 3-dimensional helicopter and ground scanning LiDAR. So fairly complicated image here showing the principles of LiDAR, which we have covered in another lecture. So basically we're using helicopter-borne and ground-based scanning LiDAR systems, and there's data processing that is done on the ground, and there is a whole series of steps of collecting, analyzing, and distributing that data. So drone technology is new and rapidly developing, and it can produce very high-density 3-dimensional point cloud data as shown here. So for example, it could have 1,000 points per square meter. It allows for repetitive measurements. It allows for intense and repeated sampling up to daily resolution. It could even be hourly or any other time frame if you were the drone operator and wanted to fly that. And again, it's a rapidly developing technology. There are many new rules and regulations that are trying to catch up with the explosion of drones into not only the private sectors, but the public markets as well. Vertical exaggeration is a concept where a scale is used in raised relief maps, plans, and technical drawings. And it's think of it as a cross-section perspective, and its purpose is to emphasize vertical features. And these might be too small to identify relative to the horizontal scale. So this has to do with the size of our map and what we're trying to show and display in our map. And so sometimes we need to use vertical exaggeration in order to really show those features. So this is an example of a z-value on the left times 1, and then if it's exaggerated times 5, you can see that crater is really standing out, and then the valleys are very prominent, the darker areas, the burgundy or rust color. On the right, we have an example of a bike ride, and if it were just laid out in the top example, there's no vertical exaggeration. With the 5x exaggeration, we can now see some change in elevation, and then the 50x vertical exaggeration is really just showing dramatic changes, and it's not representative of the real world, but it is useful for displaying some data sets. When we think about hyperspectral versus multispectral capabilities in models, this is a representative spectra for terrestrial landscape, and this was collected on the Avaris sensor. And you can see that this is showing foliage, soil, and water spectral signature curves, and then the diagram on the right is just showing you representative areas of collection. So in this case, the 3 land cover types are separable. So we are familiar with the concept of pixels, and it's the same spatial location with various bands representing different portions of the electromagnetic spectrum. So in this example, we are introducing a new term, mutually registered pixels, and you can see that it is the arrow is drawn through that 1 pixel from the blue band, green band, red band, and near infrared band. And this concludes 2-dimensional and 3-dimensional models. Thank you.